In this lesson, we're going to cover power series and also interval of convergence and radius of convergence. Our first definition, it says a series of the form, and we have sigma n starts at 0 goes to infinity of c sub n times the quantity x minus a to the n. This is called a power series in x minus a, or a power series centered at a, or it's also referred to as a power series about a. So when we have x minus a, so like for example x minus 5, the power series is centered about 5. Or if it says x plus 3, the power series is centered about negative 3. And then we have c sub n, those are our coefficients. X is your variable, and then a is a constant. This theorem says for a given power series of this form, there are 3 possibilities. The series converges only when x equals a, and then r, the radius, is equal to 0. The series converges for all x, so r, the radius, is equal to infinity. Or there is a positive number r such that the series converges if the absolute value of x minus a is less than r, and diverges if the absolute value of x minus a is greater than r, where the number r is called the radius of convergence of the power series. So prior to this lesson, for all of our series, we've identified whether they're convergent or divergent, and now we're taking our series of this form and we're going to identify the x values over which it converges. So again, when it says x minus a, the power series is centered about a. So we have a right here on the number line, and then r, the radius of convergence. From a, we add r and we subtract r, and it creates an interval which describes the x values over which this series converges. And then all the x values outside of that interval is where this series is going to diverge. And that leads us into this last definition. The interval of convergence of a power series is the interval that consists of all values of x for which the series converges, or its domain. This example says find the radius of convergence, r, and the interval of convergence, I, of the given series. Part A, we have sigma, n starts at 0, goes to infinity of negative 1 to the n, x to the n, all divided by n plus 1. So to find the radius and interval of convergence, we're going to apply the ratio test. So we have the limit as n goes to infinity of the absolute value of, and then it's going to be a sub n plus 1 divided by a sub n. Okay, so first I have a sub n plus 1. So anywhere there was an n, I plugged in n plus 1, and you can see that on the top. And then right here, n plus 1 makes n plus 2. And then next we're going to divide by a sub n, which is this expression. And instead of dividing by it, we're going to multiply by its reciprocal. Okay, so we have everything set up. A couple of things. Right here you have negative 1 to the n plus 1, and then you have negative 1 to the n. So technically the negative 1 to the n and negative 1 to the n cancel, and then you would just be left with negative 1 to the 1. But because the entire expression is inside of an absolute value, that will take care of the negative 1 that's left. I broke up the x to the n plus 1, so we have x to the n times x to the 1. So now these are going to cancel. And then at this point, 2 things are going to happen. First, we still have absolute value of x, so I'm going to bring that to the side. And then you have n plus 1 over n plus 2. So as n gets larger and larger in the positive direction, the absolute value of the n plus 1 and n plus 2 is just going to be itself. So it's still going to be n plus 1 and n plus 2. You just won't need the absolute value around it. All right, so then the next thing I want to do is this limit is with respect to n. So we can think of this x over here like a constant, and we can move it to the front of the limit. So now we can evaluate this infinite limit because it's a rational function and the degree in the numerator is equal to the degree in the denominator. This limit equals the ratio of their leading coefficients. So the leading coefficient on top and bottom are both 1. So this limit is equal to 1 over 1, or just 1. And so now we just have the absolute value of x times 1, which is just the absolute value of x. Okay, so back to the original problem, it says to find the radius of convergence and the interval of convergence. We applied the ratio test. We took the limit, the absolute value of a sub n plus 1 divided by a sub n. We worked down the limit, and what we got was the absolute value of x. So by the ratio test, to be convergent, this would be our L, and we set it less than 1. And by doing so, now this is creating an interval. Because this just says x inside of the absolute value, and also because up here we have just x being raised to the power of n, this series is centered about 0. So we put 0 on our number line right in the center, and because it says absolute value of x is less than 1, we're going to go out 1 in both directions on the number line, and that creates our interval. So you can see that our interval of convergence is going to be from negative 1 to positive 1. And then I wrote it out by the ratio test. This series converges when x is between negative 1 and 1. All right, so at this point, we know the series converges in between -1 and 1, but we get to check, yay, if the series converges specifically at -1 and +1. So we're going to check the endpoints. So first we're going to check the endpoint x equals -1. And by doing so, what that means is we're taking -1 and we're plugging it into the original series for x. So when you plug in -1 for x, you get this expression. And then in the numerator, when you have -1 to the n times -1 to the n, you leave the base the same, so you leave it as -1. And then you add the exponents, so 1n plus 1n makes 2n. But if you plug in 0, then 1, then 2, and 3, and so on, you get 0, then 2, then 4, then 6. And raising -1 to 0 or -1 to any of those even powers, you just get +1. So now we have this series of 1 over n plus 1, and we need to figure out if this converges or diverges. So to do so, we're going to use the limit comparison test. So for the limit comparison test, you take the limit as n goes to infinity of a sub n divided by b sub n. So this is a sub n, so I have 1 over n plus 1, and b sub n is the dominant term on top and the dominant term on the bottom, so that's going to be 1 over n. So I multiplied by the reciprocal, which is times by n over 1. And since this is a rational function where the degree in the numerator is equal to the degree in the denominator, our limit equals the ratio of their leading coefficients. So this equals 1. And 1 is greater than 0 and finite. So that means both the series of a sub n and the series of b sub n will do the same thing. They both either converge or they both diverge. So here's our series of b sub n, and this is a harmonic series, so it diverges. You can also use the definition of p-series, where p equals 1 and 1 is less than or equal to 1. Therefore, the series diverges. So therefore, by the limit comparison test, the series 1 over n plus 1 also diverges. So again, that means that when x is equal to -1, the series diverges. And we'll come back to that in a little bit. So next, we're going to check the endpoint x equals +1. So again, that means we're going to take +1 and plug it in right here for x. So that means right here we have 1 to the n, and 1 to the n is just 1. So you can rewrite this series as -1 to the n over n plus 1. And now you'll notice this is an alternating series, so we can use the alternating series test to determine whether this converges or diverges. So for the alternating series test, remember b sub n is the part of this series that doesn't alternate, so that's going to be the 1 over n plus 1. And then as you plug in 1 for n and 2 for n and so on, the terms are going to get smaller. So b sub n decreases. So next we take the limit as n goes to infinity of b sub n, and as n gets larger and larger, this fraction is going to go to 0. So by the alternating series test, this series converges. So again, when the endpoint is x equals 1, the series converges. So since this is called the interval of convergence, you're describing all the x values over which the original series converges. So we would say that the interval of convergence is from -1 not inclusive to +1 inclusive. So we have our interval is -1 open bracket to +1 with a closed bracket. And our radius of convergence that goes with this interval is the length from the center to an endpoint. So that would be r equals +1. All right, so there we go. For part B, we have the series n starts at 1 goes to infinity of n to the n times x to the n. So because both of these have powers of n, we're going to use the root test. So we have the limit as n goes to infinity of the nth root of the absolute value of n to the n x to the n. So I rewrote the nth root as the power 1 over n. So remember, when you shower the power, you multiply. So we're going to go n times 1 over n, and then we'll do that here as well. So when we do that, you just get n, and we can take this n out of the absolute value because it says n is going in the positive direction, and the absolute value of a positive is still itself. So I wrote just n right here, and then the x is still going to be in the absolute value. So we have absolute value of x. With respect to this limit, n is the variable, so we can pull this absolute value of x to the front. And then we have the limit as n goes to infinity of n. So n is going to grow without bound, so this goes to infinity. And according to the root test, if you take the limit and you get infinity, then the series diverges. So I wrote that out, therefore by the root test, the series diverges. So then for the interval of convergence and radius of convergence, we then write I equals, and then you use set notation of 0, and your radius of convergence is also 0. Part C, we have sigma n starts at 1 goes to infinity of x to the n over n 3 to the n. Because both of these terms have a power of n, we're going to use the root test. Okay, so I got that set up. So I took the nth root and rewrote it to the power of 1 over n. So now we can shower the power. So n to the 1 over n, those are going to cancel and just make 1. Same thing here. And then technically this n has a power of 1 on it. So when we multiply 1 times 1 over n, it's going to leave a 1 over n right here. And then also I left the x inside the absolute value, and regarding the expressions with n, since n is going in the positive direction, you can drop the absolute value. Next, I'm going to bring this absolute value of x to the front. As n gets larger and larger, this exponent goes to 0, so you have n to the 0 is 1, and then what we have left is 1/3, so the limit of a constant is just equal to that constant. So at this point, because it's the interval of convergence that we're trying to find, we're going to set this less than 1. And then when you times both sides by 3, you get the absolute value of x is less than 3. Because x doesn't have a value next to it, that means this series is centered at 0. And it says less than 3, so we're going to go out 3 in both directions. So we go 3 and -3. So our interval of convergence is from -3 to +3. So next we're going to check the endpoints. Okay, so we're going to check -3, so that means we're going to take -3 and plug it in for x into our original series right here. So I plugged in -3 for x. Next I'm going to split up this -3. So -3 is the same as -1 times 3, and then I split this up as -1 to the n times 3 to the n, and by doing that we can cancel off these 3 to the n's. So we end up getting the series -1 to the n over n. So we're going to use the alternating series test. So for the alternating series test, b sub n is equal to 1 over n. So you can see as you plug in 1 for n, then 2, then 3, and so on, b sub n decreases, and the limit as n goes to infinity of b sub n equals 0. So therefore, by the alternating series test, the series converges. So next we'll check the endpoint x equals +3. So we're going to plug in +3 right here. And when you do that, you can see that this 3 to the n and 3 to the n are going to cancel. So we just have the series of 1 over n. And you can either use the fact that this is a harmonic series, or you could do p series where p is equal to 1 and 1 is less than or equal to 1. Either way, the series diverges. We can now write our interval of convergence. So it's going to be -3 inclusive to +3 with an open parentheses. And our radius of convergence, again, it's the distance from the center to the endpoint. So it's going to be +3. And I have that written right there. For part D, we have sigma, n starts at 0, goes to infinity, of n cubed times the quantity x minus 5 to the n. So we're going to set up the ratio test. Okay, so we have the limit as n goes to infinity, the absolute value, and then this is a sub n plus 1 divided by a sub n. So first thing I want to do is look right here at this x minus 5. We have x minus 5 to the n plus 1, and then down here we have x minus 5 to the n. So the x minus 5 to the n gets canceled out, and you're just left with x minus 5 to the 1. So I left that inside the absolute value and moved it to the side, and then we can drop the absolute value from the expressions with n. Next, I'm going to move this to the front of the limit, and then because both n plus 1 and n have a power of 3, I just rewrote this as n plus 1 over n, all raised to the power of 3. So since we have a composition of functions, I'm going to take the outer function and move it to the outside and take the limit of the inside function. And then we can do this a couple of ways, but the first thing I'm noticing is it's a rational function. The degree on top is 1, the degree on the bottom is 1. Since the degrees are the same, then this limit is equal to the ratio of their leading coefficients. So we have 1 raised to the 3rd power. So we end up getting the absolute value of x minus 5. So now we're going to set this less than 1. Alright, so this is now a little bit different than the previous problems. We have the absolute value of x minus 5, and if you look at the original problem, it's parentheses x minus 5 raised to the power of n. So this problem is centered at 5, and because it's centered at 5 and it's less than 1, we're going to go out 1 in both directions. So when you go out 1 to the right, that's going to be 6, and when you go out 1 to the left, that's going to be 4 on the number line. So our interval of convergence goes from 4 to +6. So first we're going to check x equals +4, and that means we're plugging in +4 right here for x. So we plugged in 4 for x, and now we'll go 4 minus 5 is -1 to the n. So we end up getting the series -1 to the n and then n cubed. So since our terms are going to get larger and larger and they're going to oscillate from positive to negative, we're going to use the test for divergence. So when we take the limit of -1 to the n times n cubed, because the terms are getting larger and bouncing from positive to negative, this limit does not exist. So therefore the series diverges by the test for divergence. So next we're going to plug in x equals 6 into the original series. So we end up getting n cubed times 6 minus 5 to the n. So 6 minus 5 is just 1, and 1 to the n is just going to be 1. So we just get the series n cubed. So we're going to do the test for divergence again. And so the limit as n gets larger and larger of n cubed, this is going to grow without bound. So it's going to approach infinity. So therefore the series diverges by the test for divergence. So our interval of convergence is going to be from 4 to 6, not inclusive. Okay, so I wrote that out, and then also our radius of convergence is the distance from the center to one of the endpoints, so that's going to be r equals 1. Okay, so there's our final answer. And for part E, we have the series x minus 1 to the n all over n to the n. So we're going to use the root test. Okay, so we have the nth root of the absolute value of our expression. Because both of them have a power of n, since we have the nth root, these n's are going to cancel out with the nth root. So it just leaves x minus 1 and n, but I left the x minus 1 inside the absolute value. I brought the n outside of the absolute value because it's positive. And then finally, I'm going to bring this expression to the front. And then at this point, this limit is going to equal 0. So this expression times 0 just equals 0. And 0 is always less than 1. So by the root test, the original series converges. And since we didn't just get an interval over which it converges, we just get that the series ultimately converges, we say that the interval of convergence is going to be all real numbers. So it's from negative infinity to positive infinity. And then we say that the radius of convergence is just infinity. Alright guys, thanks so much for watching, and please subscribe to my YouTube channel, Math with Yosh, and hit the like button on this video or leave a comment, and hope you guys all have a great day. Take care.